All right, good afternoon, guys. So by now, I think 3/4 of you should have written test 1. How is it? It's good. It's fair to say that it's very similar to the sample test? Okay, so that's how it's always going to be. So this should serve as proof that you really should do the sample tests. Last time we started talking about proofs, and we were in the middle of going through a bunch of different proof techniques. We're going to continue doing that today. So the last proof technique we saw was to prove that something is not true, and that was the counterexample. We're going to switch gears and go back to proving that things are true. So the next type of proof that we'd like to see is what's called a uniqueness proof. This goes hand in hand with the existence proof we saw last time. So remember, an existence proof proves that some object exists, some object with some particular properties exists. A uniqueness proof will do the same thing, but go one step further and say not only does that object exist, but no other object of that type exists. So it exists, but it's unique. All right? So we'll see examples of that. So to prove an object is unique, you first have to prove it exists. And you can do that constructively or non-constructively, although typically if you're going to prove that it's unique, you tend to do it constructively. Okay, so suppose that the object is X. So you've sat down, you've done an existence proof, and now you know that the object exists. Well, what you have to do now is show that it's unique. And one way to do that is to prove that if Y is not equal to X, then Y does not have the property. So notice that's proving an implication is true. Another way to do this that's exactly equivalent is to prove that if Y does have the property, then Y equals X, because that's the contrapositive of that implication, and therefore it's the same thing. All right, so those are the two common ways to doing that. So as an example, let's do one of these things. If P is an integer, then there exists a unique integer Q such that P plus Q is 0. All right, so I know that this is going to be a uniqueness proof because it says unique in the statement. Another way to say that would be there is exactly one, or something like that. Something that says that there can only be one of these things. All right, so you do two things. First, you prove that it exists. And there's nothing wrong with labeling the parts of your proof. Right? It just makes it easier for someone to see that you know what you're doing. So the first thing you do is you prove that it exists. All right, so to prove that it exists, let Q equal minus P. And then P plus Q is just P plus minus P, which is P minus P, which is 0. So for sure, if I let Q be equal to negative P, then it does the job. It fulfills the requirements of the equation. It really is equal to 0. But what I haven't shown is that negative P is the only thing that works. Right? So if you have 5 and want to subtract a number to get to 0, there's only one number that does the job. Right? So that's the same as adding a negative number. Only one number will get you to 0. So intuitively that's true. A bit more rigorously, we now prove uniqueness. That's the second step. So the way you do that is you prove that if you have some other value that's different from minus p, then it doesn't satisfy the property. Okay? So you can do that a number of ways. One is to do a direct proof of that statement. Another would be to do an indirect proof of that statement, or you can prove it by contradiction. Yeah?
Could I ask, after you wrote p plus minus p, what is after it? Did you say p times p?
No, this is p minus p. Yeah. Yeah. All right. So what we'll do is we'll suppose that p plus q is 0 and p plus r is 0, and that they're different. Right? So if there really were two solutions to this equation, it would be these two, q and r, and they would be different, right? Because that's what it means to have two solutions. All right, so let's see what happens as a consequence of that. Well, if p plus q is 0, well, p plus r is also 0. And that must mean that p plus q is exactly equal to p plus r. Right? Because two things that are equal to the same thing are equal to each other. That's the transitive property, and we'll come back to that later in the course. So two things that are equal to the same thing are equal to each other. So if p plus q equals p plus r, well then we can subtract p from both sides to get q equals r. And now we look back at what we've written. We have q does not equal r, and we have q equals r. So this is a contradiction. You can't both have q equals r and q does not equal r simultaneously. Something must be wrong, and the only thing that was wrong was our assumption that there really were two distinct solutions to this equation. We assume that, we got a contradiction, so our assumption has to be wrong, and there are not two different solutions to this equation, which means there's a unique solution. So it's two things. We proved that it exists, and we proved that it's unique. Any questions about a uniqueness proof? This is okay? All right, so moving on. At this point, we've seen all of the proof techniques we need for now. We'll come back later and see some more, but for now we've seen enough. So what I'm going to do at this point is some examples of proofs using all of these things. All right. So here's one example. If x and y are rational, then x to the y is rational. So, if you just see the implication, you should assume that it's prove or disprove. So you don't know in advance if this thing is true or false. So what you're going to do is probably try a few values to see if it's probably true. If you think it's probably true, then start doing a proof, whether it be direct or indirect, by contradiction, by cases, whatever you feel like. And either that proof will go through and you'll be happy, or you'll get really stuck and you'll start to think, oh, maybe this isn't true. I should try some values and see if I can maybe find a counterexample with a bit more effort. So, looking at the statement, is this true or false? Which direction should we go? Yep?
It's false, because you could set x equal to 2 and y equal to 1/2.
Okay, so let's set x equal to 2, y equal to 1/2. All right, and if we do that, then x to the y is equal to 2 to the power 1/2, and that's more commonly written as root 2, right? Anything to the power 1/2 is just the square root. And we already know that root 2 is irrational. We've already done a proof of that. So we know that we're done. We know that this statement is not true because we found a counterexample. this thing here, these values for x and y, that is a counterexample. So notice that in the statement that we were trying to prove or disprove, it wasn't completely obvious that it was a universally quantified statement. But it is, right? If x and y are rational, that's saying somewhat informally that if x and y are any two rational numbers. So this is a universally quantified statement, and we found this case where it doesn't hold. That means it's false, because it's universally quantified. If it's true, it has to hold for everything, and it doesn't hold for these settings of x and y. Right? So this is a counterexample. If you tried to prove it, you would end up with something like this. You would say, okay, well, x equals a over b, y equals c over d, x to the y is equal to a over b to the power c over d, and you're stuck. Right? It's not clear what to do next based on what we've covered in this class. So if I didn't know immediately that this was going to be false, I would probably write something like this, and now I wouldn't know what to do. I wouldn't know what to do. All right, so I need to rely on the fact that I have some experience with proofs, and I already know that some numbers are irrational, and root 2 is an example of that. All right? Any questions about this? Okay, so let's see another example. In this example, I want to prove if x is an integer and x cubed plus 35, I'll write that again just so it's clear, x cubed plus 35 is odd, then x is even. Okay, does this seem plausible? Should we try some counterexamples, or should we try to prove that it's true? Yep. Okay, so if you believe that it's true, then yes, I would suggest doing an indirect proof, because the thing on the right of the implication is simpler than the thing on the left. For sure. Okay? So it's not obviously wrong, right? This isn't obviously false just on the face of it. Because, for example, I don't know, if x equals 2, then 2 cubed is 8, plus 35 is 43, which is an odd number, and x, which was 2, is even. So it seems like this is plausible. The first thing I tried wasn't wrong. So I think to myself, okay, well, maybe let's try to prove that it's correct. So let's do that, and let's do it indirectly, because of this observation that the right side is simpler than the left side. So if I wanted to prove this indirectly, I would prove if x is odd, then x cubed plus 35 is even. Because notice when you take the contrapositive, this whole thing gets negated. And the other thing that could happen would be, or x is not an integer. But we're not interested in that case, right? Because we already know that x is odd, so it doesn't make sense to consider the case when it's not an integer. All right, so if x is odd, well, we assume that x is odd because we're doing an indirect proof. So assume x is odd. Then x equals 2k plus 1 for some integer k, because that's what an odd number looks like. All right, so now we know something about x, but we'd like to know something about x cubed plus 35. So x cubed plus 35 is equal to 2k plus 1 cubed plus 35. And that's kind of annoying to do, but we can figure it out. Does anyone know what 2k plus 1 cubed is? So you can expand it out, and if you want to do that, that's fine. 2k plus 1 times 2k plus 1 times 2k plus 1 plus 35. So what are we going to get with the k cubed? So we have a 2k, 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 so we're going to get an 8k cubed. Okay, what are we going to get with the k squared? Six. So what you get is actually 12k squared. And if you don't see that, that's okay. There's a short way to do these, but you can always do them by doing it the long way. That's completely fine. And I'll just say the rest is plus 6k plus 1. Oh, plus 35. Okay. Fine. So what happens next? Do you guys see how to expand this out, or should I actually do every step? Okay, I'm seeing confused looks, so let's do every step to make sure we know how to do this, because this is an important skill to have. All right, so if you want to do actually every step, what I would suggest is doing them one by one. So we have just these two here is 4k squared plus, so we take this one and this one to get 4k, plus 2k, plus 2k, plus 1. And then we still have this 2k plus 1 out here. Is that okay with everybody? Okay. So now we simplify this to be 4k squared plus 4k plus 1 times 2k plus 1, and we still have that 35 out there. That's okay. I'm just adding 2k and 2k. So now I do the exact same thing. I'm just going to give myself a little bit more room here. So we have 2k times 4k squared, which is 8k cubed. 2k times 4k, which is 8k squared. 2k times 1, which is 2k. And then I have plus 4k squared plus 4k plus 1. And then I still have this 35 out here. Is that okay? All right, so now I just need to clean this up a little bit. I have an 8k cubed, a 12k squared, a 6k, and then a plus 1, and I still have that plus 35 out there, which is exactly what I had before. So it's okay if you don't know the fast way. There is a fast way to do this using the binomial theorem, which we used to teach in this class, but we don't anymore. Worst case scenario, just write it out by hand. I wouldn't give you a big long one like this on a test, of course. I don't expect you to be able to do this math in your head or anything like that, but this is what you do. All right, so now that we have that, we need to work with it a little bit. Let's combine everything together to get 8k cubed plus 12k squared plus 6k plus 36. And now notice what we're going for. We're going for x cubed plus 35 is even. And it's looking good because 8 is even, 12 is even, 6 is even, and 36 is even. So I should be able to factor a 2 out of all of these things. And in fact, I can. I get a 2 out in front, and then 4k cubed plus 6k squared plus 3k plus 18. And if k is an integer, then this thing is some integer. And so 2 times that integer will be an even integer. Does everyone see how I did that? Question? Can I do what, sorry? I divide 36 by 2 because 2 times 18 is 36. Other questions? Yeah? So you can just say it is because it's very simple. The only time I would insist that you give some indication why it's an integer is if it were a division, right? Because then you rely on the fact that it has to divide evenly. If you're just doing multiplications and additions and subtractions, then for sure you can just say that's an integer without any issue. Yeah. Other questions? All right, so great, we're done. Let's do another example. if x is rational, then 1 over x is rational. Is this going to be true or false? Any thoughts? False? True. Okay, so who says it's true? Who says it's false? Who says it's neither true nor false? Brave. Okay, so those who say it's false, if you claim that it's false, the way you show that is with a counterexample. What would your counterexample be? Yep. So x is 0 over anything. So let's say 0 over 1. All right, so if x is 0 over 1, then 1 over x is 1 over 0 over 1, which is 1 over 0. Is 1 over 0 a rational number? No, it's not defined. So, if that is not defined, then 1 over x must not be defined, and therefore it's certainly not rational. Right? If it's not defined, there's no way that it's rational. Is there a statement that's very close to the statement that is true? Yep. Right, so if x is any rational number except 0, then this is true. And I'll show you. So this is not true. As another example, if x is rational and x is not 0, then 1 over x is rational. And I know that because, well, if x is rational, x equals a over b, where a, b are integers, and b is not 0. And since x is not 0, what do I know about a? A is also not 0. Now, 1 over x is equal to 1 over a over b, which is equal to b over a. And I know that a is not 0. So a and b are integers, and a is not 0. And I also know that b isn't 0, but that doesn't matter, right? The only thing that matters is the denominator is not 0, and it's not, right? Because a is not 0. All right? So this is why it's very important to pay attention to the universe of discourse, right? Now, in this particular case, the universe of discourse is narrowed by the implication anyway, but you need to pay close attention to what the allowable values are. If I restrict it to non-zero rationals, it's true. If I don't restrict it to non-zero rationals, if it can be any rational, then it's false. So it's really important to pay attention to exactly what the claim is stating. Any questions about these two proofs? Yeah? So the question is, why can't b equal 0? And the reason is, if x is a rational number, you already know that the denominator can't be 0. Otherwise, it's not rational. Right, but in the last one, the denominator of x is 1. Yeah, so you need to start with a valid number. Other questions? All right, we'll move on to another example. So here's a neat one, because it's not as explicit about what the math is. You sort of have to come up with it on your own. And it's this. So between any two rational numbers, there is a rational number. So no matter what you do, you can give me any two rational numbers you would like, and I can find another one that's strictly between them. So if you give me the rational numbers x1 and x2, I can give you back a rational number that's greater than x1 and less than x2, assuming you gave them to me in order. And notice that it's strictly greater than and strictly less than. It's not greater than or equal, and it's not less than or equal. It's greater than and less than. All right. So does this seem like it's true or false? True, false. Okay, so people who say that it's false, you'd have to give a counterexample to show that it's false. What would a counterexample of this be? 1 and 3. So in this example, I could give you back 2, and that's strictly between them. Right? It's less than 3, and it's bigger than 1. Any other possible counterexamples here? Minus 1 and 1. So minus 1, 1, 0 is strictly between them, and 0 is rational. Other possible counterexamples? Yeah? So I did specify 2 rational numbers, and you only gave me 1 rational number. So it's a little bit ambiguous in English, but when I say that you're given 2 rational numbers, they should be different, because otherwise you're just given 1. If I said, if x and y are rational numbers, then there is a rational number between them. In that case, I would agree with your counterexample, because I didn't say anything about how x and y relate to each other. But by saying given 2 of them, that implies that they're different. Yep. So if I got 1 and 2, I could give you back 3 halves. Yep.
What about something like 1 over 100 and 1 over 100?
1 over 100, 1 over 101. Any thoughts? 2 over 201. So is that definitely, so 2 over 101? 2 over 201? Okay, so is that going to work? Why will that work? Okay, so this is 2 over 200. This is 2 over 202. And you're giving me 2 over 201. Is that definitely going to be between them? Yeah. Yep.
Could we say 1 over infinity is 0?
So
we can't really define it.
Yeah, so the issue there is 1 over infinity is not a rational number. Yeah. Okay, so what does it, so we've tried a few counterexamples, and we're not getting anywhere, because anytime we try a pair, we figured something out. Yeah? Sorry? Root 2 is, but root 2 is not rational. Yeah. So we've tried a few counterexamples, and we always get stuck because we can always find a number. What number are we finding? So when we were trying to do 1 and 3, we came up with 2. When we tried to do minus 1 and 1, we came up with 0. When we tried to do 1 and 2, we came up with 3 halves. What are we really returning? Yeah? Right, and what's another word for that? The average or the mean. The median is different. So it feels like we want to do something with the average. So maybe the average will do the job. So what we'll need to do is prove that the average of the two numbers is always strictly between them when the numbers are different. So let's try that. Let's try that. So let's say let x and y be 2 rational numbers with the understanding that they're distinct. So with x not equal to y. Okay? And in fact, let's assume that x is less than y. Is that a fair assumption? Yeah, so I'm not assuming too much here. You're giving me two numbers, and I'm calling the smaller one x. And that's always valid because you're giving me two numbers that aren't equal. So one of them has to be smaller. I'm saying let's call x the smaller one. Right? And if you didn't give me the numbers in that order, well, I can just rearrange them so that that would be the case. There's nothing special about the order of the numbers. I just need to know what it is. It can be whatever you want as long as I know. All right. So x is the smaller number. X is less than y. All right. So since x and y are rational, we have a couple of things. We have that x is equal to a over b, and y is equal to c over d. Notice I'm not using the same numerator and denominator both times. The very common mistake is to say x equals a over b and y equals a over b. You can't do that because if you say that, x and y are equal, but we already know they're not equal. Right? So you can't use the same numerator and denominator. And what do we know about these things? We know that a, b, c, and d are integers. And we know that b and d are not 0. That's what we know about the world so far. And the approach we're going to take on this is to look at the average of the two numbers. Right? That's our plan. So we're going to define z to be the average. All right, so z is equal to x plus y over 2. Right? That's the definition of the average of two numbers. So let's work out what exactly this is. X plus y, well, x is just a over b, y is just c over d, and this is all over 2. So far, so good? All right, so we're adding two fractions that have different denominators. So what we have to do is find a common denominator, and the common denominator is BD, B times D. So what we get is AD plus BC over BD, and this is, again, still all over 2. Right? I know that because I multiplied this by D over D, and this by B over B. So I get a B with the C and a D with the A. Is that okay? All right, so then the very last thing to do is to simplify this. This is just 1/2 times the top, so that's just AD plus BC all over 2BD. All right, so what we have to do now is we have this Z, and notice that this is really just an existence proof. Right? I'm proving that there exists a number between x and y, a rational number between x and y. So what I have to do is give you the number, if I want to do it constructively, and I do, and I've given you the number, it's z. So now I have to prove that z satisfies all of the things I want it to. And in this case, there's three things. The first is that z is rational, and the second is that it's between x and y. So really, it's bigger than x and smaller than y. Yep?
Wouldn't you have to first add x to it so it'll be smaller than x?
What do you mean it'll be smaller than x?
Because the average of 1 and 2 is a half.
The average of 1 and 2 is 3/2. Right? It's 1 plus 2 is 3 over 2. 1.5. Yeah. All right, so now I need to show that it's rational. So is z rational? Well, the numerator is AD plus BC, and I know that's an integer. An integer times an integer plus an integer times an integer is definitely an integer. And 2 times BD, which is the denominator, I know that it's an integer, because 2 times an integer is an integer. Do I know that it's not 0? Yeah, so why is it not 0? Right, b and d aren't 0, and if you multiply together 3 numbers and none of those numbers are 0, you know for sure that the product won't be 0. Right? The only way you can get a 0 in a product is if one of the things you multiply is 0. So I know that it's an integer and it's not 0. So z is the ratio of two integers, and the bottom integer is not 0, which means it's rational. So therefore, z is rational. Okay, so now I need to prove that it's really in the range I want. So I need to show, well, I'll phrase it like this. So is z between x and y? That's what I need to do now. Okay, and notice that, that this really is the order because I assume that x was smaller than y. So I have to do two parts to this, really. I need to do this part here, and I need to do this part here. That's the easiest way I know how to do it. Okay, so let's start with the first part. I want to prove that z is bigger than x. All right, so to prove an inequality, what you do is you start on one side of the inequality and work your way to the other side. So I know that z is equal to something, right? Z is equal to x plus y over 2. That was the definition of z. Okay. And I want to prove that z is bigger than something. What's something that's definitely bigger than x plus y over 2? Yeah? X plus y is bigger, for sure. But the issue is it's not clear what to do after that. So what can I do instead? Yep. So that will give me a bigger number. I want to get a smaller number here, though, right? X over 2, yes. But that would show that z is bigger than x over 2, and I want to show that z is bigger than x. Yep. So I'd like to show that it's greater than x, but I can't quite get there directly. I need one step in the middle. Here's the step. I'll just say this. X plus x over 2. How do I know that that is true? Yep. Yeah, y is greater than x. So y is greater than x. So when I'm working with these inequalities, I'm allowed to replace things like that. Y is bigger than x, and I know that because of this. Y is bigger than x. So I can replace y by x to get something smaller. All right, so all I'm doing is substituting in an inequality I know. This is just like substituting in an inequality, except you need to keep the direction of the inequality straight. All right, so it's a little bit trickier, but it's the exact same idea. And now I can say, okay, great. Now I have x plus x is 2x, and I have 2 on the bottom, so that's just x. 2x over 2 is x. So what I showed was that z is greater than x. Right? That's all I had to do there, and that's all I did. Z is greater than x. Any questions about how I did that? So we're going to work with inequalities quite a bit in this course, and it's important to be comfortable with doing this kind of thing. So if this was surprising to you, you need practice working with inequalities, come talk to me, I'll give you some exercises. But you need to be able to do operations like this. All right, so that's only half of it. We also need to prove the other half. I need to show that z is less than y. And to do that, I do the same basic trick. Well, z is just x plus y over 2. And that is definitely less than y plus y over 2, right? Because x is less than y. And that's just 2y over 2, which is y. So, therefore, z is less than y. And now I've proved both things, right? I've proved that z is bigger than x, and z is less than y. Therefore, it's strictly between x and y. And I've proved that there's a rational number, and I know it's rational because of this, and that it's between x and y, and I know that because of all of this. Questions about this proof? So if you're going through a proof like this and you get stuck, for whatever reason, make sure that you write out the steps that you wanted to prove. Right? So even if I wasn't able to make these last leaps with the inequality, at least write out what you wanted to prove. At least write out, I want to show that z is bigger than x. I want to show that z is less than y. If you couldn't figure out how to show that z is rational, just write out, I want to show that z is rational. Right? Because a big part of this is knowing what you have to prove, even if you're not always able to do it. Question?
How do you say that x plus y over here is less than y plus y over here?
This right here? Yeah, so that's because of this. X is less than y. That relies on the fact that x is less than y, and I know that x is less than y because that's right there. So that's how I derived that. It's the same trick as in the previous one. Other questions? All right, so now that we have that, let's do another example. So I want to show the real number equation 5x plus 3 equals a has a unique solution. Okay, so to be clear, a is a constant and x is the thing I'm solving for. So a is just some constant, x is the thing being solved for. All right? So I want to prove there's a unique solution, x. Okay, so basically this is saying a line crosses a horizontal line at one point. All right, so first you have to prove that it exists. And I know that it's a uniqueness proof because of this word unique. So I know I have to do two parts. I need to do existence and uniqueness. So I first do existence. All right, what do you think the solution would be to this equation? Yeah, it's going to be a minus 3 over 5. A minus 3 over 5 is the solution. All right? Does everyone believe that? Okay, it's true, because what happens if you sub in a minus 3 over 5? So let's do it. 5 times a minus 3 over 5 plus 3. Well, the 5's cancel. The minus 3 cancels with the plus 3, so you get a, which is exactly what you wanted to get. Right? So that's why it's a solution. Oops, I spelled existence wrong. All right, so the next part that we do after existence is uniqueness. So we know that this solution exists. Now we have to prove that it's unique. So to do that, we suppose we have two solutions. Let's call them x and y. Or no, let's not call them x and y. We already have an x. Let's call them s and t. All right. Well then, 5s plus 3 equals a. And 5t plus 3 equals a. Right? That's what it means to be a solution. And since they're both equal to a, we know that 5s plus 3 equals 5t plus 3. Right? Because two things that are equal to the same thing are equal to each other. All right, so now we can cancel a plus 3 from both sides to get 5s equals 5t. And we can cancel a 5 from both sides to get s equals t. So is this a problem? Yeah, so if we have two solutions, then they should be different, but I just showed that in fact they're the same. Therefore, the solution is unique. All right? You don't even need to go to a proof by contradiction for this. This just shows that if you have solutions s and t, then s equals t. Question in the back? What if a was equal to plus 3? So a equals plus 3. So we want a solution to 5x plus 3 equals 3. Yeah? Okay. So then the solution that this gives us is 3 minus 3 over 5, which is equal to 0. And that makes sense because 5 times 0 is 0 plus 3 is 3. Other questions? Yeah?
I was wondering if the last example, is logarithm defined for complex numbers?
You can do things like log for complex numbers, yeah.
Then wasn't there an example like log of square root negative 1 over log of square root negative 1 proves that's wrong?
Right, but those aren't rational.
But if you simplify it, then it becomes rational, right?
If you so you're saying the log of I?
The log of I is the log of I.
Right, but this assumes that x and y are rational numbers. Maybe I don't understand your example. We can talk after. All right. Other questions about this uniqueness proof? Yeah? You could, or you could say that if you have the solutions s and t, then they're equal. So if you wanted to do it like a proof by contradiction, then yes, you would write they're not equal. The way I've written it here says if you have two solutions, then they're equal. So you're not really looking for a contradiction at that point. The distinction is kind of subtle, doesn't really matter. Other questions? All right, so you've made it through proofs. Congratulations. The next topic in the course is sets. So I'll warn you now, it feels like we're about to move on to something completely different, but as you'll see by the end of class today, sets are basically the same thing as logic. So we haven't seen the last of that stuff. So we've actually talked about sets quite a bit already, even though we haven't explicitly said what they are. I think most people have a good understanding of what a set is. So for example, the universe of discourse that we've been dealing with is a set. A set is an unordered collection of objects. That's what a set is. So the objects that you have inside of a set are called the set's elements or members. Okay, and they're usually listed inside braces. When we want to talk about the members of a set, we have some notation. We write X is an element of A to mean X is inside the set A. All right, that's how we use that notation. All right. we have an example of a set, and let's say it's 1, 2, 3. This is a set, and it has 3 elements. They happen to all be integers, but that doesn't matter. It's exactly the same as the set 3, 2, 1. It's exactly the same. There is no difference between those two sets because sets are unordered, as we saw up here. Right? Sets are unordered collections. So what that means is that order does not matter. Another set that is exactly the same is 1, 1, 2, 3, 3, 3, 3. It is the exact same set. And that is because repetition also does not matter. All right? Repetition does not matter in a set, and order does not matter in a set. Typically, all the objects that are in a set are of the same type. If you want to think like you're in a programming language, they'll all be integers, or they'll all be colors, or they'll all be names, or something like that. But there's no such restriction. So typically, all objects in a set are the same type. Whoops. But they don't have to be. So for example, 1, 3, red, blue, John is a perfectly good set. Although I don't know why you would ever define a set that way, but you can if you want. Sometimes when you're defining a set, you don't want to explicitly write out every single thing in the set because that's kind of a pain. So you can use ellipses when the pattern is clear. So for example, if I wrote down 1, 2, 3, 4, ... 50, the only thing that would make sense is if this were the set of all integers between 1 and 50 inclusive. All right? So there are some sets that we use a lot. They come up a lot in math, so we have some short notation for them. So some sets we use a lot are the following. The set R is the set of real numbers. We also have the set N of natural numbers. We also have the set Z of integers. And we also have the set of rationals that we've been spending a lot of time talking about. It's the set Q. Okay? So these are some commonly used sets that come up a lot, so we have nice short names for them. All right? If you're wondering how to write these, pretend you're writing on a blackboard and with the side of your chalk. So for example, Z would look like that. That's why we do this weird notation. It's for historical reasons, because professors used to not have nice tablets. They would write on the blackboard, and they wanted some way of distinguishing between what was a set and what wasn't a set. So that's why we have this notation. All right. It's possible to have a set with no elements. Okay? And if you wanted to do that, you would write curly braces with nothing in them. And that means it's a set that has exactly 0 elements in it. It's somewhat common, so we also denote it like this, an O with a slash through it. It's called the empty set. Oh, sorry, it's usually called the empty set and denoted that way. Usually called the empty set. One thing you should not ever do is confuse that as this. That is not the same thing. So this thing here, this is a set that has one element in it, and that single element happens to be a set. And then that set has no elements. So the size of this set is 1. There's one thing in it, and that thing happens to be a set. It's perfectly valid to have a set that consists of sets. But it's not the same as the empty set. And you know it's not the same as the empty set because they have different sizes. So 2 sets that have different sizes, right away you know that they can't be the same. Does everyone understand that distinction? All right. Yep. Right, so there's this notion of subsets that we'll get to, yes. Yes, so the empty set has precisely one subset, and it's the empty set. Well, so, I mean, the statement has nothing to do with subsets. The statement is whether this thing is equal to the empty set, and it's not. So it's true that the empty set is a subset of that set, but it's not equal to that set. But we'll talk about subsets shortly, probably next lecture. All right, so this brought up the idea of the size of a set, so let's formalize that a little bit. The number of distinct elements in a set S is called its cardinality. And it's usually denoted with absolute value bars. So you would say the size of S. And it's usually clear from context whether this means an absolute value or a cardinality. Right? It means a cardinality if the thing on the inside is a set. It means an absolute value if the thing on the inside is a number. Okay? You can have the case where the size of S is infinite. So if the size of S is infinite, so for example, if you're talking about the set of integers, there's infinitely many, we say the set itself is infinite. All right, so the integers are an infinite set, the rationals are an infinite set, and so on. Okay. One common way to define a set is with set builder notation. So what you would say is, for example, the set R of real numbers, you could define it as all numbers R such that R is a real number. Right? The set O, you could define it as all O such that O is an odd integer. Right? It's just a shorthand way of writing these things so you don't have to fully write it out. If you're familiar with Python, This is a list comprehension, essentially, except, well, it's for a set. Python, in fact, does have set comprehensions, in case you didn't know. But it's the same idea. You say what object you want to have in your set, and then a bar, or in Python, it's, what is it, 4, and then you say what properties you would like that object to fulfill. Questions? Yeah?
Can a set be an element of itself?
Can a set be an element of itself? That's an interesting question that we'll come back to in a little bit when we talk about subsets. Yeah? Other questions? All right, so now I've defined what sets are. So the next thing we'll do is talk about the things you can do with them. And those are the set operations. So these are operations you can perform on sets. The first one is the union. So given two sets A and B, the union is the set of all elements that are in either A or in B. So given two sets A and B, the union of A and B is written A and then a cup and then B. So it's like a little letter U, but without a tail or anything like that. And it consists of elements that are in either A or B. So either A or B or both. Both is fine too. It's not an exclusive or. So as an example, if I had A as the set 1, 3, 5, and B as the set 2, 3, 6, what is A union B going to be equal to? 1, 2, 3, 5, 6, right? It's everything that's in either set. Okay? All right, so if we wanted to write this using set builder notation, we could say that A union B is equal to all x such that x is in A or x is in B. And it's not a coincidence that the symbol for union is very, very similar to the symbol for disjunction. Unions are like ors because something's in the union if it's in this set A or that set B. Okay, this is how you would reason about that using set builder notation. There is indeed an and equivalent, which we'll talk about in a second. Before we do that, I just want to talk a little bit about Venn diagrams. And we'll get into this more later. So if you have two sets like this, you can talk about where the union is. Okay? So the union is everything that's in either set. So it's all of the elements that are here and all of the elements that are here. Right? So it's everything in A and everything in B. It's not too important to understand Venn diagrams yet. I just want to introduce them here so when we do them later, you've seen them before, even if you're not sure about how they work. All right, so the next type of operation you can do is intersection. So this is when you take two sets and look at what's common between them. So given two sets A and B, the intersection of A and B is written A cap B. So it's an upside down union symbol, if you like. and it consists of the elements that are in both A and B. Okay, so as an example, if A was 1, 2, 3, 4, and B was 3, 4, 5, 6, what would A cap B, A intersect B be equal to? 3, 4, right? Those are the elements that are in both of the sets. All right. So, if again we wanted to go to set builder notation, A intersect B is equal to all elements X such that X is in A and X is in B. And just to make sure that we all understand this is different, it's that. Okay? And notice that the symbol for intersection is a rounded version of the symbol for conjunction, because intersection and conjunction are similar kinds of operations. All right, if we wanted to look at the Venn diagram for this thing, which again, if you'll bear with me, I'll define later. We have A and B, and the intersection A intersect B is all the stuff that's in both of them. So it's all the elements that live there in the middle. Any questions about intersection? Yeah?
Does the box kind of represent like the university of Bitcoin?
Yeah, it's a similar idea. I'll define that more thoroughly in a second. Yeah?
So is another set being created, like 3 or 4, like an intersection, and then those are being put into another set?
So they're their own set. So it's just like if you add 3 and 4, you get this number 7. It's not really a new number, it's just a number. Other questions? Yeah? Yeah, so I'll do that later on when I talk about negation. For now, it's not that important to understand it. We'll come to that soon. All right, so the next set operation that I want to talk about is the difference of sets. So, given two sets, A and B, the difference, and I'll call it A minus B. So when you're subtracting sets or taking the difference of sets, some textbooks just use a regular minus sign. I like to change it up a little bit and use this sort of slash, like a backslash. I like to do that just because it keeps my symbols distinct. Right? You can see clearly that I'm not subtracting numbers, I'm subtracting sets because it's a different symbol. So the difference A minus B is the set of elements in A but not in B. All right, so notice order matters now. Right? It matters if it's A minus B or B minus A. That's important. A minus B is the set of elements in A but not in B. Okay? So as an example, if A was 1, 2, 3, 4, and B was, say, 3, 4, then A minus B is what? 1, 2, exactly. Right? I take out 3 because it's there. I take out 4 because it's there. So I'm left with 1, 2. All right. So in set builder notation, A minus B is equal to all X such that X is in A, but X is not in B. So as usual in math, if we want not in, we just write in with a slash through it. Right? That's the standard math pattern. Okay? If you wanted to be more explicit, you could write X in A and not x in B if you wanted to, but you certainly don't have to. Right? The critical thing is that you understand that it's not in B. Okay, so if we wanted to go to a Venn diagram, we have the set A here, the set B. I'll make this a bit bigger. The set A here, the set B there. And the difference is everything that's in A but not in B. So it's this. It doesn't include the middle part because that's in B. Does that make sense? All right. So sometimes A minus B is denoted A minus B. I think the textbook might do it that way. I prefer this other way because I don't like to reuse symbols whenever possible. All right. So there's a couple more things. The next one is what's called the complement. And this is kind of like negation. So given a set, you can also look at all of the things that are not in that set. So given a set A, the complement is the set A bar and consists of all the elements not in A. Okay. Now that only makes sense if you've defined some universe that you're drawing the elements of A from. Right? If I said the set of all students not in this room, that only makes sense if I've defined the entire set of students. Okay? So to define this, to define this, we need some definition of the universe of all possible elements. And typically we denote this U, although some textbooks denote it by S. Doesn't really matter. So really, you can view the complement as a special case of set difference. So complement is really just set difference. So the complement of A is just the universe minus everything in A. Right? So if you had the set of all integers as your universe, and A is the set of all odd integers, then A complement is just the universe minus A, which would be all x such that what? So x is an even integer. Is 0 an even integer? Yeah, it's 2 times 0. All right. So that's how you define that. And again, you can do this using set builder notation. So A bar is equal to x such that x is not in A. You could also write it is not the case that x is in A. That would be just fine too. Or you could substitute it into the definition for set difference. The very last operation, so I should do the Venn diagram first, sorry. So here I'll only do one set A, and this box that I've been drawing but not labeling, that's what U is. So the complement of A is everything outside of A, as you would expect. I'm not going to fully shade it in, but you get the idea. Okay? So the last operation I want to talk about is kind of a weird one, and it's the Cartesian product. And I'm going to define it here because it makes sense to define it here, but then we're not going to use it for a while. So you'll have to refer to this again later. So given two sets A and B, whoops, the Cartesian product of A and B is denoted A cross B. So that's the same symbol you would use for something times something. And it's the set of ordered pairs where the first element of the pair is in A and the second element of the pair is in B. Okay, so it's easiest if you do this from by example. Before I do that, I'll do the set builder notation for it. A cross B is the set of all pairs AB such that A is in A and B is in B. Little b and big B. All right, so as an example, if A is the set 1, 2, 3, and B is the set AB, then A cross B is the set of all ordered pairs where the first thing is from A and the second thing is from B. So I'd have 1A, 1B, 2A, 2B, 3A, 3B. Right, that would be that set. And notice that order matters, because if it were B cross A, then the first element would be from B and the second element would be from A. Okay. So you can't do a Venn diagram for this one because A and B are being drawn from some universe, but A cross B is not in that universe because A cross B consists of ordered pairs from each of those universes. This will come in very handy later when we talk about relations, but for now we don't care too much about it. All right, so we'll stop here for today. Next time I'll continue talking about sets.